Now we're going to take a look at the general response of an underdamped second order system. So we determined previously that the homogeneous solution for the second order underdamped system is going to be something that looks like this. We're going to have an oscillating function, a trigonometric function with a phase shift to it potentially, as well as the exponential function that's decaying right here. So we can really think of this as two separate functions, as the product of two separate functions. We have the exponential function, and we have some sine wave with an amplitude of f and some phase shift. So I'm going to plot those two, and then we're going to combine them together, think about what they would look like together. So the first function right here is the exponential function. So at time equals 0, this one is e to the 0. So this is e to the negative squiggle omega n t. It's going to be identically equal to 1 at time equals 0. And then we know that this is a decaying function, right, and it's going to decay down towards 0. All right, so as time increases, it's going to asymptotically approach a value of 0. All right, so in that case, we see that this squiggle omega n is like our is related to the time constant of this would be like a first order system response, and that's squiggle and omega n is going to determine how quickly this function decays. The larger the value of that product, the faster it's going to decay. Okay, now we're going to take a look at the f times the sine function here of omega dt plus phi. All right, we're going to assume that our initial condition here are such that we have no phase shift, which may or may not be the case. It just depends upon the initial conditions of the system. And we're going to plot the sine wave. Now the sine wave is going to look like a sine wave that has an amplitude of f. All right, so the sine wave starts at 0 and it continues to oscillate between f and negative f. For the amplitude, and that's going to continue on forever and ever. So now we're going to take the product of these two right here, and the result for the second order system is that we're going to see oscillations that decay with time. So if I take the product of these two, we're going to have some large value initially, some large overshoot, and then the amplitude of those oscillations are going to decay with time. How the amplitude decays with time depends upon this e to the negative squiggle omega n function. So that provides sort of the envelope that defines the maximum value, or the values at these maximum points. The other thing that we need to look at is what is the frequency of the oscillations, or what is the period of the oscillations. And we see that that is defined by this damped natural frequency term right here. So a complete oscillation is going to occur within within 1 omega d. So how fast the oscillations occur depend upon this damped natural frequency value. So if we take a look at varying some different parameters here, we can see that if we have a large damping ratio, right here where our damping ratio is close to 1 for the blue line, the oscillations are going to decay very quickly. If we have a system that starts at some non-zero value and it has a smaller damping ratio, we're going to see the oscillations continue for a longer period of time at a higher amplitude, and still yet if we have an even lower damping ratio, the oscillations are not going to damp out as quickly. We also see the effect of the stiffness of the system. If we increase the stiffness of the system as we go from a k value of 1, which is the blue line, to a k value of 3 to a k value of 6, we see that the stiffness of the system is going to impact the oscillation frequency. So that's also going to impact the damping ratio as well. But the oscillation frequency is determined primarily by the ratio of the stiffness of the system to the mass of the system, whereas the damping is determined by the damping ratio, or the resistance or friction that remains in the system. Okay, so we can see that we can change a lot of parameters here, and they're all going to have related effects to each other. But the primary one that determines the frequency is going to be related to the stiffness or the spring constant of the system, whereas how quickly the oscillations decay are going to be related to the damping of the system, or the C value. Okay, so in conclusion, what we can expect from a second order system that is underdamped, we're going to see oscillations. The oscillations are eventually going to decay to some final steady state value, and the oscillation frequency is going to depend upon the damped natural frequency of the system.